Okay, so this chapter, kinematics in 2 dimensions. This obviously follows the structure of kinematics in 1 dimension. That was chapter 2. And the rules that we learned in that chapter are still going to apply. This is mostly going to be applications so that we are kind of understanding how to track motion in a plane as opposed to just a single dimension. Because even the objects that were rolling down a ramp or sliding down a ramp, we could tilt our coordinate system so that the ramp had or the x-axis of our coordinate system lined up with the ramp, so that we could collapse that into 1 dimension. But there are other types of motion, namely projectile motion, which is going to be the topic of this week's lab, that you just can't collapse into 1 direction. So we need some time to practice splitting horizontal kinematics from vertical kinematics. So I kind of have a note here just asking us to think back to our earliest definition of average acceleration. So this dates back to like the last part or the later parts of chapter 1. If we have a motion diagram for an object and we sketch in position vectors that we use to figure out the orientation of velocity vectors, our next step would be to figure out what the change in velocity vector delta v should be. If we divide that by our time interval, what we have is now the average acceleration. So in other words, if you know the direction of delta v, you also know the direction of a. The same way that knowing the direction of a displacement vector delta r automatically told you the direction of an instantaneous velocity vector v. So when we're talking about velocity in particular, you can kind of come up with 2 ways, one obvious, one less obvious, that an object can experience an acceleration. And the first point here is clearly the most obvious of the 2. If you are in a car that's going from, let's say you are at a light that's just turned green, you're going to go from 0 miles per hour to maybe 25 miles per hour over the course of a few seconds. So your speed is changing. And even if we assume that your car is just pointed in a straight line, so you're not turning at all, the acceleration that you experience in that scenario is completely due to you going from slow to fast. However, you can also accelerate in a scenario where you maintain a constant speed, but you change the direction. Like you are, let's say you're turning onto a highway on-ramp. And let's say that you're that person who doesn't speed up as you get to the on-ramp. So let's say that you just do maybe 35 the entire way, so that by the time you get there, you're moving way too slowly to merge into traffic. But just for the sake of discussion here, if you maintain that speed of 35 miles per hour, the fact that your car is changing direction, that you're turning your steering wheel, also means that you're accelerating. And that is ultimately what's responsible for like the acceleration that sometimes you can feel in the pit of your stomach if you are traveling over a bridge that's curved, or if you are on a roller coaster going through a section of track that is curved, or if you are, let's say, the passenger in the car that is either going onto an on-ramp or off of an on-ramp, and it kind of feels like you are getting nudged to the side. That acceleration is just the result of your car changing its direction. So you may or may not actually speed up or slow down while that's happening, but the point is that you can still accelerate even if you don't speed up or slow down, just because of the change in direction. So imagine that we've got a character, Maria. She's on a Ferris wheel. And let's imagine that this motion diagram describes what happens after the ride actually begins. So in other words, imagine Maria is the last person to get loaded on, so that once she's on, the Ferris wheel just completes the trajectory like we see here at a constant speed, no stopping and starting, in other words. If we were to take snapshots of Maria's position at different points but consistent intervals, around the trajectory that she's tracing out, we would see that as long as her speed is the same, these velocity vectors will all have the same magnitude, but from one moment to the next, the direction of the vector is going to change. So even though the Ferris wheel can be traveling at a constant speed, Maria is continuously accelerating. And we can figure out the direction of her acceleration by calculating this delta V vector, just like we did for our linear trajectories when we were talking about just a car driving in one direction. The difference here is that the acceleration vectors are going to point like toward different regions on my, or they have different coordinates or different, if I broke this acceleration down into an X and a Y coordinate, they would change from point to point. I would be able to find a location, or if this motion diagram were labeled differently, if the intervals were a little bit different, I would be able to find sometimes where Maria's acceleration is completely horizontal, and then other times, like we see here, where her acceleration is completely vertical. So in the sense of a Cartesian coordinate system, these vectors are not all pointing the same way, but in a radial coordinate system, they are, because toward the inside of her trajectory is radially inward. That's true for all the points around this trajectory, even though the arrows are not all pointing the same direction in a Cartesian sense. I'm getting a whole bunch of email invites to like a semester's worth of meetings, so I'm sorry if that chime is audible for you. But anyway, so Maria is accelerating, but not because her speed is changing, simply because her direction is changing.
So her speed's not changing, but her velocity is changing.
Yes.
So thus, because the velocity is changing, she's experiencing acceleration.
Right.
Okay.
Okay, so here we revisit our a-parallel, a-perpendicular notation that we saw for the first time in our discussion of objects on an inclined plane. So for an object, let's say that's sliding down a ramp, there's one component of the acceleration that is responsible only for making that object go from slow to fast. And the other component is only responsible for changing the direction that that object is moving. So when I say changing the direction, think about it with or in relation to free fall. So if that plane wasn't there, if the ramp wasn't there, then this object would just drop straight down. But because the ramp is there, it slides along the surface of the ramp. So its direction is being changed by the presence of the ramp underneath it, if that makes sense. So that would be like our A perpendicular that controls direction. A parallel is controlling the speed. So for Maria on the Ferris wheel, A parallel would be 0, but A perpendicular point toward the center of her trajectory. For, let's say, a car that is accelerating from rest along a flat section of road, A perpendicular would be 0, because the direction of the car is not changing with respect to like the direction of free fall. And a parallel is going to be non-zero because it's responsible for making the car go from fast to slow. And it's possible for general cases like the one that we see in the inset to be true, where a parallel and a perpendicular are both non-zero. So that's kind of like what would happen if we were trying to consider what happens to Maria if she's not the last person to be loaded onto the Ferris wheel. So let's say that she's the first person and she's got to go through a whole lot of stopping and starting while everyone after her is being loaded on the Ferris wheel. When she's going from not moving to moving and moving along the segment of the circle, the arc, her acceleration would be, going too far here, would be like this kind of dark orange arrow here. There'd be a parallel part and a perpendicular part that add together to some net acceleration A. Okay, so we, on our very first day, we talked about 4 different types of motion. Rotation is one we're not going to be ready for a while, so we can put that on the back burner. But we had translational motion, so only left or right, or only up or down, or only back and forth. You had circular motion, which was exactly what it sounds like, a trajectory that overlaps itself. And then the third one was projectile motion. So that is an object that moves horizontally at the same time that it moves vertically. So let's imagine that we were drawing a trajectory for some object. It could be like a basketball that you're trying to, if you're trying to make a free throw, let's say. This graph here is not just position versus time, but it's like a position versus position. So this is exactly what you would see if you took a video of someone making a free throw and you plotted out how the horizontal and the vertical positions were changing over time. So to say that another way, I've got 2 times that are shown here. T is equal to 1, matches up with this position right here. T is equal to 2 is just sometime later that matches with this position there. So if I am just working off of a standard Cartesian coordinate system, my initial position vectors are going to come from the origin to point 1 and then the origin to point 2, where the displacement, like the middle of the story, the part that we would use to make a judgment about the average velocity that the object has, is going to depend on this delta r vector, where I could figure out what this delta r vector is by measuring how the vertical change in position changes from 1 to 2 versus how the horizontal position changes from 1 to 2. And I could quite literally use the Pythagorean theorem to figure out what the magnitude of this delta r vector had to be. I can recognize that v average vector is something I can split up into component vectors that lie along the x and the y axis. So the interval of time separating points 1 and 2, that's constant. So that's just going to be our delta t that shows up in the denominator of both terms. But now the magnitude of that velocity vector is going to depend on the ratio of delta x over delta t, or delta y over delta t, where I'm using unit vector notation again right here, the I hat and then the j hat directions. So I initially had, let me blink back here, look at the separation between points 1 and 2 now compared to here. So what we are imagining here is that we are letting the interval of time, delta t, approach 0. So in the limit that delta t shrinks and shrinks and shrinks, we're getting velocity vectors that are that pertain to progressively smaller instants in time. So we're going from like the big picture view of what's happening to that basketball during the free throw to an instantaneous view of how quickly the basketball is moving at any point along that trajectory. So in the limit that delta t approaches 0, this delta r vector divided by delta t becomes dr dt, or the derivative of this position vector, where I can split that position vector into an x and a y component, and I have now dx dt and dy dt. So those are my components. I multiply those by the unit vector for the appropriate directions. I can rewrite this as the velocity in the horizontal direction, because dx dt is just the velocity in that direction. Dy dt is also a velocity, but vertical. So this velocity is going to be vx I hat plus vy j hat. Now, comparing these images here.
Quick question.
Yeah.
So, we're computing the slope here by doing this, obviously, because we're doing the derivative. So we're looking at, like, this is 1 point. Like, we're looking basically for the slope of the point at 1, right?
Right. You're imagining drawing a tangent line and then computing the slope of that line.
Okay. So what is that in relation to 2? So we need the 2 points and be able to get the delta r and to be able to take the limit of it. Is that what's going on here?
Yeah, well, we're kind of going from we need 2 points for the interval. So think of the position at t2 at 2 as being like t final. So
Okay.
our goal is to collapse T final and T initial into the same number so that you end up with a vector that describes only one instant in time.
Right.
So the position of T2 kind of becomes less and less obvious visually as you're collapsing it down because you are trying to come up with an interval that effectively has zero length in a temporal sense, so that
Right.
your velocity vector applies to just one point on the curve as opposed to two, when in reality it's kind of like two overlapping points.
Gotcha. So you need you need at least 2 points, or you need 2 points to be
You
able to
need
do
two
that.
points, but your goal is to keep the first one stationary and then shift the second one so that they occur at the same time.
Gotcha. And so like as you're like going from this far right point of 2 all the way as you go here, does that velocity vector like change?
It does. It becomes more and more, I guess, accurate, or it becomes more indicative of what's happening at a narrower range
At point
of the
run
story.
at point one rather than at, so it becomes more indicative of what's happening at point one rather than at point one versus point two.
Or you're less concerned with what's happening between points 1 and 2 and more concerned with what's happening at point 1.
Gotcha. Yep. Okay.
Okay, so this green vector from this slide is the same as this one here. So we've isolated our instantaneous velocity vector. We want to decompose that just as we did in our chapter 3 practice problems. So
So,
we
sorry, quick question again. When you
sure,
get that velocity for that green vector, that's the magnitude, or it's both? Does it have both magnitude and direction?
it has magnitude and direction.
Okay.
So the magnitude we can find just by applying the Pythagorean theorem. The direction, we have to make a decision about our coordinate system. And luckily we made a choice way back here about where our X and Y coordinates were, or our axes were relative to one another. So now our angle theta, again, this is kind of arbitrary choosing to draw it with respect to the horizontal axis, but if I am defining with respect to the horizontal axis, this needs to be theta. So the horizontal component of this vector is v cosine theta. The vertical is going to be v sine theta. So we end up with this conclusion here. So we're kind of thinking about the magnitude of this vector as being equivalent to the like the hypotenuse of the right triangle that we could draw centered at this one point here. So to say that another way, this is if this was the Pythagorean theorem, C would be the velocity, then Vx and Vy would be A and B respectively. For a magnitude, we would just take a vector magnitude, we would take the square of the component, the horizontal component, add it to the square of the vertical component, and then take a square root. So like these two operations that we previously kind of thought of as doing different jobs, they're really doing exactly the same job here. We can kind of think about it from either direction and be correct in both senses. And just as we did here in chapter 3, once we make a decision about where theta is, we can use the tangent of that angle to figure out or we can use the tangent, so the ratio of Vx and Vy in some form to figure out what theta is.
Quick question.
Yeah.
So if you like, my thought was like, if you look at these light green component vectors, it's almost like it's creating an entirely new like graph, right? Where it starts at the origin instead of like starting at some point on the regular Cartesian what we have here. So
So
at
you
any
mean like
time,
this point being the origin of a new coordinate system compared to this one?
yeah.
That's what you mean? Okay.
And so like, I don't know, I guess, so that's sort of basically what's happening. So like in terms of like the Vy and the Vx, like are those magnitudes? Like, is it sort of thought of in that sense where it's like it's starting from yeah, I guess because we're doing the Pythagorean theorem. So
Yeah,
it's not like the Vy starts from like some point like out of for X, you know, in the middle of the original coordinate system. It just starts from 0.
yeah, the way that, right. So if you were to measure the magnitude of this Vy vector, you wouldn't start way down here at the original coordinate, the original origin, but exactly what you said. Yeah, so it's like you are using your original Cartesian coordinate system to determine how the Vx and Vy vectors that come from the solid green vector, how you can decompose that to get these light green vectors. But the way that it's written here, we have Vx and Vy in terms of their magnitudes. We could absolutely make these into vectors. So where our Vy vector would be it's not labeled as such here, but vertical component of V is just Vy vector, and horizontal component of V is just the Vx vector. So you do kind of have two overlapping coordinate systems in a sense, but think of the light green one as a consequence of a decision that you made earlier about
Gotcha.
the X and Y axes.
I think I'm gonna benefit from an example because I haven't quite made the jump from like what we are like making the limit of, I guess, and like what the result of that is gonna be. Like in terms of like how do we get from the limit do we get the X component and the Y component is basically what I'm not quite connected with yet.
Okay, so I think you will benefit from seeing the problem or a problem solved, but think of it like this for the time being. You are starting with a large interval of time between 1 and 2. You want to progressively shrink that down so that your interval really becomes just representative of one point in time where the delta t is equal to 0. Once you have collapsed that interval down so that it's describing just one point in time, now you can draw a tangent line. You can determine what the slope of that tangent line is. That would give you the magnitude of the instantaneous velocity at that point. And then you can go back to your X and Y axes, a choice that you would have had to make a lot earlier in this problem, and then figure out how to decompose that solid green vector into these light green vectors.
Okay.
And that just also involves choosing one of these interior angles to be your theta. In this case, it's the one relative to the positive x axis.
All right. I think I'm going to benefit from an example.
Yeah, we'll just check back in once we get to the example. And if there's anything that we need to backtrack and kind of connect, I'm happy to do that. Okay, so we're still doing pretty good on time. Okay, so now just to be clear, we're still working off of the same vector in green here. And we're imagining now that we do this process again, but for a point or a time that is centered back on our original t is equal to 2. So I think I might have, okay, so not our original t is equal to 2, but one of our later t is equal to 2. The one that is kind of at the apex of this trajectory right here. So we'll draw a tangent line. We will figure out the slope of that tangent line to get the magnitude of that v2 vector. We can define an angle theta. It's not really shown here, but we can split this v2 into a v2x component and a v2y component. What we are really concerned with for this slide, though, is figuring out what the average acceleration vector is, how it needs to be oriented. And we can go back to that first slide from this half of the chapter and remind ourselves that if we can find delta v vector's direction, the average acceleration vector is going to be the same. Because our delta t is a scalar, it can't do anything to change the orientation, just shrinking or stretching the vector. So I want to subtract v1 from v2. So first make a copy of v1 that is oriented the opposite direction. So, or add that negative copy to v2, and I get a delta v vector that's pointing down and to the left like this. So not straight down, but down and to the left. And it's not outright stated here on this group of slides, but this is a more realistic, it's like a more realistic representation of a somewhat low mass projectile. And I say somewhat because, or that's just a way of saying a projectile that is affected by air resistance or affected by drag. The ones that we're going to work with in lab this week are by no means unaffected by drag, but they are compact, they're relatively high mass for their size, so the impact of air resistance is going to be really low. But if we were to instead like compare a solid metal ball to a ping pong ball, something that's hollow, it's got a bunch of air in it, it can be large, but it's not very massive. You would be able to see the effect of drag hitting or impacting the ping pong ball a lot more easily than you would be able to notice drag impacting the solid metal ball. So this here is like a realistic representation instead of an idealized one of how a solid metal ball would behave. It would experience some drag that would cause its acceleration to not be pointing straight down, but down and a little bit to the left because this object is generally moving rightward along its trajectory. This average acceleration has got to be the first derivative of the velocity function that we could write for this object. Or in other words, if we have a velocity vector that we defined on the previous slide, so like a v1 and a v2, we could combine those two together to figure out what the delta v vector would be, and then divide that by delta t. And as we let delta t approach 0, we're working our way from an average acceleration to an instantaneous one. Because there are, it's not really marked out here, and I don't think I have that. Yeah, I don't have that image on the next slide coming up. But let's think about what this average acceleration vector would look like if I had a third velocity vector that matched up with some part of the trajectory over here, but I wanted to calculate the acceleration between 1 and 3. So I'm skipping over 2, imagining that I have a 3 over here, where vector v3 is going to be pointing down and toward the right. At the highest point in the trajectory, this acceleration vector is going to be closer to pointing straight down. So in an idealized case, it would point straight down. There would be no drag to worry about. So that acceleration at that point in time would collapse from this average acceleration that's down and toward the left into one that is just straight down. And that's kind of what is being communicated here by this new image, where this is the same average acceleration vector. I think my scale was a little bit off. I apologize for that, but this vector is still pointing down and to the left. I'm going to decompose that into an x and a y component. Again, a consequence of a choice that we made a lot earlier. And this acceleration in an idealized case, ax would be 0. So that this solid orange arrow and the a sub y component would coincide with one another. The reason why that's not happening in this image here is because it's because of like a slight difference between the hypothetical scenario that we talked about on this slide, imagining that there's a 0.3 over here and then finding the average between 1 and 3. That centers on the highest point in this trajectory. That's not the case for this one here. So this object is still moving up a little bit. So there is going to be a component of the acceleration that is oriented toward negative x that causes the sum of ax and ay to be a little bit bigger than just ay by itself. But the point here ties back to something that we encountered in the second half of kinematics in 1 dimension. So the second half of chapter 2, when we were talking about how to go from an like a graph of velocity versus time forward to an acceleration versus time graph, or to go from velocity versus time backward to a position versus time graph. And if you're going forward, you calculate slopes or take derivatives. And that's exactly what's happening here. I can take the derivative of this velocity vector, break it down, so I'm worrying about the x component all by itself and the y component all by itself. And when I join them together, I end up with this solid or this dark orange acceleration vector that again applies to just this one point in the trajectory. It will be different for the highest point in the trajectory, and it will be different for an earlier time before it reached this higher point. So when this object was probably moving a bit faster because it hadn't been slowed down by Earth's acceleration. So to combine that with our unit vector notation that we just saw in chapter 3, I can, instead of expressing that acceleration as an an A parallel or an A perpendicular, I can decompose it and express it as AX and AY using unit vector notation here. So I want to skip down to this little kind of shaded image down here at the bottom. These are kinematic equations. Instead of being written for the generic S axis, they're written for the problem that we've been kind of working through. So let's say we want to figure out the change in horizontal position for that, what we were calling it, free throw. I think we were saying that this was representative of a free throw. We could figure out the change in horizontal position for any interval delta t that we choose, provided we have knowledge of the acceleration in that direction and the acceleration that applies to that interval in time. Likewise, we can do that for the vertical direction. The time-independent kinematic equations are not shown here, but since they're the combination of the two time-dependent ones, we can also say that VFX squared has to be equal to V initial x squared plus 2ax delta s. All I've done is taken the third kinematic equation that's time independent and switched the s's in favors of x's, then do it one more time for the y's. However, if you don't have that third kinematic equation, you can still essentially track the position of any projectile using a combination of these four, looking at how the velocity changes in the vertical direction compared to how it changes in the horizontal direction, and just relate that to how the position changes in the vertical direction and how it changes in the horizontal direction. So for an idealized projectile, we're going to switch back to one that, or to an idealized scenario where drag is either non-existent because you're imagining your experiment takes place in a vacuum, or drag is negligible, which is actually going to be a good enough approximation for the experiment we're going to do later this week. So to say that another way, the only thing that's exerting a force on the object once you let go of the ball is gravitational interaction with the planet. It's not the atmosphere acting against the tennis ball for this example. It's just Earth interacting with the tennis ball. And for like the earliest parts of this conversation, let's not pay attention to the bounces, because that is an interaction between the floor and the tennis ball that's slightly different than the planet and the tennis ball. Let's just imagine what the tennis ball is doing when it's in between bounces. So it is traveling horizontally at the same time that it is changing its position vertically. And if we could imagine kind of subtracting out these four like particles, or these four snapshots of the tennis ball, and then do the same thing for the successive bounces, we can kind of clearly see that the ball does not travel up the same distance for every interval delta t, or in other words, every adjacent pair of images. It goes up quite a bit between here and here. It goes up less in successive snapshots, to the point where it is stationary relative to the vertical axis at the highest point. So in other words, it goes up as high as it can, and it's going to pause for a moment so that it can change direction and start moving down. So for any particle that's experiencing projectile motion like this, and it's only under the influence of gravity, the trajectory is going to be a parabola. Now for the, so instead of the free throw that we were thinking about a bit earlier, let's just imagine a basketball that you are like trying to bounce from one person to the other. So like a bounce pass, in other words. So as long as the court's not warped in some weird way, the initial vertical position of the ball is going to be exactly the same as the final vertical position of the ball. So we can take the same logic that we used to try to identify what the instantaneous velocity of the free throw example had to be. We can apply that to t is equal to 0. So the moment right after the ball interacts with the court, after you bounce it to your teammate, that is your velocity at time 0. Sometimes you will see, I tend to use v initial for this instead of v0, but v0 just means at the beginning of your experiment. Imagine when you are turning on your stopwatch to analyze whatever event you're trying to understand. So the point is that we can take that vector, decompose it into an x and a y component, and the magnitudes of those components can be plugged into the kinematic equations that are at the bottom of this slide that we saw a bit earlier. So here I have v0 for the x direction. That's going to be v0 cosine theta. Again, just a consequence of the fact that we chose theta with respect to the x-axis. That means v0y is going to be v0 times the sine of theta. And if we look at the acceleration, since this is our idealized case, there is no force that is acting on the basketball in the horizontal direction. So the absence of a force in that direction also sort of means that there is no acceleration in that direction. But the vertical component, Earth is still continuously trying to pull that basketball back toward the center of the planet. So there is a consistent acceleration that's acting on the ball the entire time, regardless of whether it's moving up, moving down, or not moving at all in the vertical direction. And that acceleration is going to have a sign that is a consequence of the coordinate system choice that we make. So if we say that y is positive extending up, negative extending down, the acceleration along the y-axis is going to be oriented toward the negative direction. So this is another way of saying that the horizontal speed of the ball doesn't change between bounces, but the vertical speed does change. So in other words, for every, let's say, 1 second interval, the basketball travels exactly the same horizontal distance, but the vertical distance changes. And it's not super, I guess it's kind of, you can see it in this image here. If we just take a look at this part of the trajectory between bounces, if we could measure horizontally how far the center of mass of this tennis ball is moving horizontally, you'd get the same value regardless of whether it was far from the ground or closer to the ground. So that's staying consistent, but the vertical position is changing as a result of this acceleration. Oh, so this is another example of free fall. It's really easy to think of free fall and to visualize holding something in the air and then dropping it. But this also qualifies as free fall because there's no other force acting on the basketball except for gravitation. So this trio of images here kind of seeks to take a similar scenario. So this is closer to the free throw that we were talking about earlier. And we can break it down so that in the panel on the left, we see the instantaneous velocity vectors at an equal interval. So the ball starts off with a large speed right as you let go of it. As it's moved through the air a little bit, it's slowed down some because it is not moving up as quickly as it was when you released down here. It slowed down a little bit in the vertical direction. At the highest point in the trajectory, it's not moving vertically at all anymore, but it's still moving horizontally. And then this behavior kind of starts to kind of backtrack, or it starts to kind of reverse itself. So that now instead of having a 0 vertical speed and a small horizontal speed, you've got the same small horizontal speed, but paired up with a larger vertical speed. And that will increase as the, I guess, if the trajectory allows this object to go beyond x is equal to 0. Think back to that problem that we did about tossing something into the Grand Canyon so that the initial vertical position and the final vertical position are really different. I can decompose each of those green vectors into red and blue components, the reds being horizontal. They're all the same magnitude because of the absence of an acceleration in the horizontal direction. And then the blue vectors do change their magnitude because of the fact that the acceleration is non-zero and it points down. So the ball goes from moving up quickly, if we're just looking at its vertical component, to not moving at all. And then it starts moving down quickly. We can write that in unit vector notation because we know that so for example here, if it takes 1 second to go from here to here, then here to here, that's like assuming that those times are separated by 1 second kind of requires that we have a velocity that has a really specific value. So that horizontal component would just be 9.8 times the I hat. The vertical would be 19.6 times the J hat. It's not a coincidence that there is a multiple of 2g that shows up here. Why that's a 2g is going to become evident a little bit later. But the point here is that we can completely isolate the horizontal motion and apply our kinematic equations just to that direction, and then completely isolate the vertical and apply the vertical kinematic equations to describe what's going on in that direction. And if necessary, we can join them back up to make the green vectors that are on the left. But it's not always a guarantee that you care about how those velocity vectors or how those two component vectors add together. There's a lot of value in keeping those separate. So we've got a practice problem here, at least one, that we will be able to get through. Maybe two, we'll see. So we have a ball that's moving at 0.75 meters per second, rolls off of a tabletop that's 1.20 meters high. How far will it travel horizontally before striking the floor? So just one thing to kind of highlight again before I switch over to the tablet. This point here, when we introduced these 4 time-dependent kinematic equations, the one thing that connects all of them is delta t, because the free throw is moving horizontally for the same amount of time that it's moving vertically. That's also true for the bouncing tennis ball that we saw here. And it would be true for the bounce pass that we imagined kind of breaking down here. So the delta t that shows up in the horizontal equations is exactly the same as the one that shows up in the vertical. So let's rejoin here and we can start solving this. All right. All right, so we've got chapter 4 questions here. Okay, so we know the initial horizontal speed of the ball before it leaves the tabletop. We know the initial vertical speed of the ball before it leaves the tabletop. We know the displacement it's going to undergo. We're trying to figure out the horizontal range. So just to make a real quick sketch here, we have our tabletop. We'll let this be the floor. And we have a trajectory that's going to be shaped like this. I'm going to say that at t is equal to 0, the ball is just leaving the edge of the table. So its y position is going to be 1.20 meters. I wanted to turn that to a velocity for no reason. And then down here, at some later time, it's going to hit the ground. We don't know what it is, but we can find it. And we know that the position when that happens, it's going to be 0 meters. So there are two things that are going on here. We have horizontal motion, and I guess I'll use this orange for that. Bx, or B initial x, I will say. V initial x is going to be equal to 0.75 meters per second. Then down here, V final x is still going to be 0.75 meters per second because the ball is neither speeding up nor slowing down horizontally. In other words, this is a consequence of the fact that AX is a vector with 0 magnitude. Now for the vertical direction, V initial y, it might seem like we don't know this, but we know that the ball is not moving in the vertical direction until it leaves the table. So vertically, the amount of time that it would take for that ball to go from 1.2 meters to the ground is exactly the same as what it would take if I just held an object 1.2 meters above the ground and let it fall straight down. This is a result of the fact that I know that AY is not only non-zero, but it's negative. So I'll say AY is minus 9.80 meters per second squared. This is a vector that is directed downward. I don't know what VFY is. I can figure it out, but it's not necessary to figure out what VFY is for this type of problem, and it'll become evident why in a moment. So I have two accelerations, two acceleration components. One is 0, one is non-zero. I've got two velocities for the horizontal direction. I have one velocity for the vertical direction. I have two vertical positions. And the last thing that we're trying to figure out, or the question we're ultimately trying to answer, is what X final is. So I don't know what X final is. I'll be able to figure it out. But I do know that if my coordinate system is drawn like this, let me use blue. If this is my y-axis, and this is the x-axis, the origin of my coordinate system will be right here. So the horizontal change in position is going to be x final minus x initial. X initial will be 0. All right, so we can apply the first kinematic equations that we will need to use to answer this question will pertain to the vertical direction. Then we can catch the horizontal second. So
are we looking for delta t first?
Yes, because we can find delta t based on what we know about the vertical direction. So we have a change in position. We don't have a v final. So that means that the formula that's going to help us for this one is going to be the position formula, but for the y direction. So y final is equal to y initial plus v initial y delta t plus 1/2 ay delta t squared, where our final position is going to be a 0. And since we determined that the ball had 0 initial vertical speed before it leaves the table, that whole middle term is going to go as well. And we can rewrite this as 0 meters is equal to 1.20 meters plus 1/2 negative 9.80 meters per second squared times delta t squared. So we can solve this for delta t. Okay, so we have a negative on top and negative on the bottom that are going to cancel out. Your delta t's are always going to be positives. And let's see. We will end up with a delta t of about 0.4949 seconds. So this delta t has to be the same delta t for the horizontal direction. So now let's use the horizontal kinematic equation for position. And again, since I know that the acceleration is 0, I know that Vfx and V initial x are exactly the same. That second kinematic equation is not going to be of much help to us. So x final is equal to x initial plus V initial x delta t plus 1/2 ax delta t squared, where now I can say that x initial is 0. I can say that ax is 0. So this whole last term is going to go. So x final is going to be V initial x, that is the 0.75 meters per second. And then delta t is the time we just calculated, 0.4949 seconds. And here's what we get. We end up with x final being equal to 0.3712 meters. And we've got these sig figs here. Let me look at the original. We have 2 sig figs. So x final is 0.37 meters. And just a reminder here, delta t is the same for both directions.
So you're right, we didn't need to find V final y.
Right, that's extra. So that's extra for this problem here. There are problems where you'll be asked how quickly something is moving as it hits the ground. Then just your next step would be to take your delta t and plug it into one of those velocity equations. Okay, let's see. Swap over here. And now let's take a look at this reasoning about projectile motion topic. It'll probably be where we finish off today's meeting. So note, we didn't need to know anything, or we didn't need to use the horizontal speed to figure out delta t for the problem that we just solved. It was enough to know that the table was 1.2 meters high and that this was taking place on or near Earth's surface. So we knew the acceleration. That's all we needed to know. So that means that if we were to compare these two scenarios here, imagine that you've got a red ball that you're dropping straight down. You have an identical yellow one that you are giving an initial horizontal velocity. It doesn't matter that the yellow ball is moving horizontally and the red one isn't when it comes to figuring out how much time it takes to go from whatever y initial is to ground level, which will be our y final. That just depends on Earth, really, and the height from which they are released. Doesn't even depend on the mass of the object. That is, we had a little bit of a discussion on one of our lectures from last week. I don't recall exactly which one, but about dropping like a feather and a rock at the same time, or just dropping two items that have different masses. They are subject to different degrees of air resistance, but Earth isn't pulling any harder on the rock than it does on the feather, or vice versa. So we can completely separate the horizontal part of yellow's motion to turn it right into red's motion. And like another way of thinking about this is to imagine that we were all in the lab together, that I asked you to take your phone and to record the yellow trajectory, or to record the yellow ball, but instead of standing still like we learned to do when we were first developing motion diagrams, if I let you walk horizontally at the same rate that the yellow ball is moving horizontally, you would end up with a video that looks pretty similar to this red one. So the background would be blurred because you were moving, but if your goal is to keep the yellow ball in the center of the frame and move along with it, you would just see it get closer and closer to the floor, because your walking would be canceling out the horizontal part of the yellow ball's trajectory. So this kind of hammers home the idea that projectile motion is really just another form of free fall, and you can take this two-dimensional problem and kind of collapse it into just a horizontal, or just a vertical direction and just a horizontal direction. You can't really put both of those directions together and solve at the same time. That's not to say that you can't like develop a system of equations that depends on some horizontal stuff and some vertical stuff. That's essentially what we did with that practice problem, even though I split it up into steps. But there is no single kinematic equation that will let you combine like a vertical initial velocity with a horizontal final velocity and kind of get you there in one step. You need to separate the X and the Y. So imagine that this is, so the second reasoning about projectile motion slide here. This is usually referred to as the monkey and hunter problem, but the language in our textbook changes that to a coconut, so I guess nobody is harmed in this problem. But the idea is that a hunter spots a coconut in a tree that's some distance away from them. They point the arrow at the coconut, but coincidentally, the coconut falls at exactly the time that they shoot the arrow. So in the monkey and hunter scenario, the monkey sees the hunter and then decides to drop from the branch. So you want to figure out, or we want to try to think through whether or not the arrow still hits the coconut or whether it misses. And the graph that we've got here off to the side shows a real representation of what is going to happen to the arrow, and then like a false one. So the real one down here at the bottom is the parabola. We know that the arrow is going to, and we're assuming that the hunter is at ground level, let's say, and the coconut's a lot higher. If you want to hit that coconut with the arrow, you're not just going to want to fire that arrow horizontally. You have to angle up a little bit. So what we see here, because you're trying to account for gravity is the point here. So we see the arrow go up in the air. It's going to reach a maximum vertical position, then it's going to start speeding up on the other end. So what we're imagining here with this false trajectory is what would happen if you could turn off gravity. So if the hunter fires up and there's nothing that causes the arrow to drop back down, it would just continue moving horizontally at exactly the same rate and vertically at the same rate. So instead of a parabola, you would have a line here. And while I was speaking, I'm not sure whether we can, I guess, run the video back if you care enough about that. But this actual trajectory here is assuming that the hunter and the coconut are not separated by different vertical positions, but at the same vertical position. I could change this graph to make it line up with what I think I said the first time, but I just want to make that clear that the initial vertical position of the arrow and the initial final position of the arrow are going to be the same for this graph. So now we want to match this up, the behavior of the coconut, because we've kind of explained the arrow part of this story. So The coconut is going to drop straight down. It's experiencing free fall, just like the arrow, actually, but in one dimension instead of two. So it's going to speed up at a rate that we can predict. The initial vertical velocity of the coconut is 0. And then if we say that, let's say y is equal to 0 is up here in the tree, and this position here would be negative, then the negative or vertical position of the coconut would just be 1/2 g times t squared, where the g would have a negative because our coordinate system is pointing down. I would have a negative on each side so that I would still get a positive time. But that's the assumption that we're making here. Another way to think about this is that this is just the magnitude of the operation you're doing, 1/2 gt squared.
I have a question.
So, yeah.
How much does this depend on the initial velocity of the arrow?
It depends on the initial velocity of the arrow in that so like imagine you were trying to throw a football to somebody else who was the same height as you and they're going to catch it at the same vertical position that you let go of it. You would have to account for Earth trying to slow that football down. So you would gauge how far up you have to throw the same way that the hunter would have to gauge how far up they aim the arrow. So the horizontal like component of V and the vertical component of V.
It's like the trajectory is like skewed. So like from like instead of the horizontal from the football, it's just angled for the coconut, right?
Right, and maybe a football was a poor choice because your goal is to try to, I guess, make this a pass like that as linear as possible. But unless you want the person who's catching your football to be closer to the ground than you are, you still have to account for gravity by angling it up a little bit.
I guess my question is like if like I was able to have this arrow shoot at the speed of light, would it matter? You know,
well,
like,
yeah, it would matter in that specific case.
you know what I mean?
If
Or
you
like
had the option
if
to
this arrow was
fire
going 1,000 miles per hour, would it still hit the coconut? You know?
it would, because what is relevant here is
Then the
not.
coconut would just not fall as much.
That's true. It wouldn't fall the same distance. So the arrow would get to the coconut a lot faster if you fired it really fast.
So then
But
it just needs to be enough so that the coconut doesn't hit the ground first.
I suppose, yeah, if the distance
So there's
between you and the coconut is really large, but you're limited as to how quickly you can fire the arrow, it might be possible that it just wouldn't get there.
So there
in
is like
time.
a constraint on the initial velocity of the arrow in that it needs to be enough so that it doesn't hit the ground first, you know, before the coconut's gonna hit the ground.
Yeah, in a realistic context, yes. But in the idealized one, no. Because the thing that's different about how the coconut and the arrow are like moving through atmosphere has to do with their sizes and their shapes. So they're not guaranteed to have exactly the same amount of drag. But the initial velocity of the arrow in either direction, X or Y, the final velocity of the arrow, and the initial and final velocities of the coconut are not really what's important, but how they change. And the arrow, once the bowstring has stopped pushing against it, it's in free fall. So it is guaranteed to drop or to accelerate down at exactly the same rate as the coconut.
Because of the problem, they both enter free fall at the same time. And so as long as the arrow is aimed well enough and has it at least sufficient, you know, velocity or whatever, or like you said, it doesn't matter. They're gonna hit. Gotcha.
Yeah, if you had like for some reason a sail attached to your arrow so that it was really impacted by drag, then this would start to fall apart because the arrow is not in free fall and the coconut is. But as long as you have like a well-designed arrow that is aerodynamic, then drag is not going to slow the arrow down.
Aerodynamic.
So then, yeah, aerodynamic. So the point is that both of the items are going to accelerate in the same direction at the same rate. So the amount of time it takes for the arrow to hit the coconut changes when you change the speed, but the rest of that problem stays consistent.
Right. right? So the time would be the only thing that changes then.
Mhm.
Gotcha. And so that's consistent with what we say here, because time is a variable here, and it's 1/2 GT. That's a constant, and then just time is the variable.
Right.
Gotcha.
Right, but it's going to be the same time for the arrow as you see for the coconut. And I think, okay, yeah, so just to kind of, I'll overlap this next time because I'm pretty much already out of time. But for cases where the initial vertical launch position and the final vertical position are the same, you can solve two of your kinematic equations simultaneously so that you are calculating a horizontal distance in terms of the initial speed twice whatever your initial launch angle theta is in g. I don't have this on the formula sheet because it pertains to a narrow range of scenarios, whereas if you put these four equations together, they will solve, or they'll get you through every projectile motion problem. But this one applies to a narrower range of scenarios. And then we've got a practice problem showing up here. Yeah, example 2, we'll start with this on Monday. So what do I want to do here? I need to get out of this meeting so I can stop the recording. Then I'll stop sharing here. And I'll ask, are there any last minute questions before we call it a day for today? All right, well, if not, I will see about half of you tomorrow. I'll see the other half on Friday. I hope you have a good rest of your day, and drop me a line if you've got questions or concerns about anything.
I actually have a question.
Okay.